Well, hello, I'm Rob Versluis, and I'm going to talk about benchmarking of treat reactor models. I have recently joined the Office of Innovative Nuclear Research, it's NE-42, and as Program Manager for Transient Fuel Testing R&D. Dan Wax from the Idaho National Laboratory is the laboratory counterpart for this program. This program mission is actually shared between the fuel campaign, that's NE-52, and our office. The program seeks to upgrade experimental and measurement capabilities of TREAT, and once it has been restarted. Ultimately, the objective is to improve the quality and resolution of data obtained from future fuel tests. This particular IRP is specifically directed at developing benchmarks that support the validation of better computational models for TREAT itself. All right. So here's a picture of the Transient Reactor Test Facility, better known as TREAT. In the background, you can see the Fuels and Materials Center. And TREAT is located near the center, but far away enough to be safe when something happens. TREAT was designed for transient testing of nuclear fuels and materials during off-normal and accident conditions. It was used in performing over 800 experiments from 1959 to 1994, and it supported the development and licensing of LWRs and SFR nuclear fuels. So the TREAT restart is now underway. Its transient fuel testing capability is needed again to understand and support licensing of advanced fuels such as the accident-tolerant fuels and SFR transmutation fuels. This is what TREAT looks like on the inside. It can operate in steady state and in pulse mode. The fuel actually has accumulated very little burn-up and is still quite fresh. On the right-hand side, you can see that people can stand on the reactor without really any protective clothing. On the left, you see a model of TREAT showing the core with a test vehicle in the center. It shows the hodoscope on the left-hand side and a radiography facility on the right. The hodoscope is a key measurement capability. It has 36 axially resolved fast movement detectors, and they can make visible the movement of any fuel that relocates axially during melting or some other reason. On the right is the radiography facility. It is used to check the integrity of the test fuel before the test, and again after the test if needed. This is a summary of fuel tests that were carried out in TREAT starting in the early 60s until 1994 when it was shut down, along with a number of other nuclear energy R&D facilities. It helped resolve key issues such as fuel coolant energetics, fuel failure criteria, source term issues, and so on. And it provided key data needed for code validation and regulatory approval of commercial LWR and SFR fuel. A little about the test vehicles that were used in the experiments. There are two types, the stagnant capsules and the flowing coolant loops. The stagnant capsules could be either dry and filled with inert gas or wet, filled with the coolant of interest. And they were primarily used for phenomenological, separate effects, and basic process tests. The flowing coolant loops were more sophisticated, and they were used for prototypic, multiple effects, and complex interaction tests. On the bottom you can see what type of vehicle was used for what kind of test. So accurate modeling of the test and its environment can really improve the quality of the test. In the past, each new test required a number of calibration runs, and these calibration runs served to fill in the gaps where modeling was unavailable or unreliable. Modern modeling tools, they can improve the pre-test design of experiments. They can help qualify reactor test vehicle configuration, and they reduce the number of calibration experiments needed. We need accurate treat reactor benchmark cases to validate such codes. Benchmarks will initially be based on existing experimental treat data. After restart, benchmarks would incorporate new experimental treat data in the post mode, including spatial and temporal distribution of temperature and radiation fields. An important role of treat is to obtain separate effects test data for validation of fuel models such as Bison Marmot. It's a NEMS fuel model. So this IRP is seeking applications that will develop evaluated benchmark cases to use in the validation of treat modeling and simulation codes. Key data types to include are temperature and radiation field distributions across the core and over a time frame characteristic to the transient. Use experimental data from existing treat experiments and new data using the prototype water loop now under development at INL. This IRP scope contains three major tasks. The first is neutronics benchmarks. The second is loop thermohydraulics benchmarks, and the third has to do with core instrumentation, selection, and placement. So the neutronics benchmark, in this, the idea is to evaluate existing treat neutronics calibration data. We ask that this is done in accordance with the International Handbook of Evaluated Reactor Physics Benchmark Experiments. This handbook is the gold standard of benchmarks, and here are some of the requirements that need to be addressed. It requires a detailed description of the experiment and measured data, a comprehensive evaluation of experiment parameters. It requires benchmark specifications, should address known simplification biases, and it should include best estimate calculations using contemporary nuclear codes. Eventually, such benchmarks will be available, useful, and available for code validation purposes. So, task one is on the neutronics benchmarks. It has two subtasks. Task 1A concerns itself with the steady state benchmark. This involves evaluation of existing experimental data of various kinds. It should include internal and independent reviews of the evaluation reports. And after that, submit the report to the International Reactor Physics Project in the first year of this IRP. And then prepare final reports for the handbook publication using the feedback that you got from that community. Task 1B concerns the transient benchmarks. We ask you to investigate available transient treat data to establish possible benchmark usable measurements and develop the initial benchmark. Investigate a wide range of configurations, including delayed and prompt critical transients, as well as temperature limited and shaped transients. Perform analyses with 3D neutron kinetics, and those codes should account for the temperature reactivity feedback. And then in the second year of this IRP, submit reviewed benchmark reports through the IRP-HCP to address development of the report format for such transient benchmarks. So task 2 is on loop thermohydraulics benchmarks. And for that we need loop systems with sodium and water coolant for future tests. For sodium, there is an existing recirculating loop design. For water, a completely new water loop is being designed. Task 2A, it also has two subtasks, is the sodium loop pH benchmark. Use existing data from operation of sodium test loops during previous 3 calibration runs. There's some examples mentioned here. And include loop configuration, coolant flow rates, time-dependent coolant temperature distributions, etc. And then use appropriate modeling and simulation tools to validate data that represent conditions observed in the flow loops. So task 2B on the water loop benchmark, here this IRP requires that a new prototype water loop consistent with PWR conditions be fabricated and installed. So the loop will be based on conceptual design that has been developed by INL. It started this year and this fiscal year, and should be completed in fiscal year 15. And this loop will include electrical heating to simulate the fuel impowerment. The proposal will include enhancements that address final detailed design and instrumentation as required for fabrication. Detailed information and INL technical support will be provided to our awardee. The type of data needed are configuration, flow rates, pressure, time-dependent temperature distributions, and multi-phase flow parameters as needed. Also, perform operations tests to determine optimal loop control parameters, as well as for experiment environment and the potential of running tests at steady state and transient thermal hydraulic conditions. The test results will be validated against analyses using appropriate modeling information. Task 3 is on core instrumentation selection and placement. Here we ask to identify measurement and instrumentation necessary to develop benchmark quality transient testing data. Develop a strategy for instrumentation selection and experiments to determine optimal placement of additional instrumentation. The ultimate goal is enhancing operational activities and simulation strategies. Include in the initial analytical evaluation in advance of actual experiments to support the planning of benchmark data collection. Initial analysis should also serve to develop a template for the final benchmark report after treat has been restarted and sufficient new transient measurements have been obtained. We expect uncertainty analyses to identify priority core physics data needs. This slide shows the contact information for myself and Dan Wax in 42, and Frank Goldner and John Carmack in NE-52, as well as a URL where you can get more information. And are there any questions?
Task 1A appears to be a very large task to complete in 1 year. How flexible is the overall schedule?
Well, there's always something that can be negotiated.
How can we access TREAT's past experiments database?
Dan, can you take that?
Yes, I think that if you're looking for information, a lot of it is applied technology, but it can be, we can work through that and identify the experiments that you're interested in. If we require making contact with somebody at the laboratory, and we can guide you through that process. So I would say contact me, and I'll put you in contact with the right people. And I think Rob had my contact information on the slide.
Yeah, let me put that slide back up.
Although much of the data is on OSTI as well.